Welcome, kids, crew. This is our 10.2 polynomial function notes. Let's dive right in, talk about what a polynomial function is. Right? A power function was a single term with a power of x in it. A polynomial, poly means many, is a sum of power functions. The general form of a polynomial looks like this. You see lots of sums in here, could be minuses, subtraction as well, right? But to be a polynomial function, n, which is your degree on x, has to be a positive integer. As far as terminology goes, standard form is when a polynomial is written from the term with the highest degree working down to lowest degree. The leading term is the term that has the highest degree on x. The leading coefficient is the coefficient of that leading term. And the degree of the entire polynomial is the degree of the leading term. So here's an example. I have g of x equals 3x squared plus 4x to the fifth plus x minus x cubed plus 1. I want to take that and I want to put that in standard form. So I'm going to start with the term with the highest exponent on x, which is this term here. So I'm going to rewrite this as 4x to the fifth. Then I'm going to look for an x to the fourth term, which I don't have, but I do have an x to the third. So minus x to the third. Then we're going to work down in power on x, in the exponent on x. So this is plus 3x squared, then plus my single x, that's like x to the 1. And then finally, we're going to end with our constant. Our leading term is the term with the highest power on x, highest exponent, so that's going to be 4x to the fifth. And the leading coefficient is the constant that is being multiplied by that power. The degree of the polynomial is the degree of that highest powered term, so that's going to be 5. Okay, sorry for the pause there. Had an important phone call I had to take. All right, so let's pick up and let's talk about end behavior, which we talked about in class recently. And the idea is this. So if we take this function f of x cubed minus x squared minus 6x and we graph that on a standard window, we can see that whereas a power function with a degree of 3 might look like this, that this graph has some bumps to it. So, right, it might look something like that. So we've got some bumps in it. If we change our window, it'd be good for you to do this on your calculator. So we're looking farther out, right? Going from negative to 100 to 100, and then maybe from negative 1,000 to 1,000. And then we look at that function, right? It's kind of like if you get in an airplane, as you take off from the runway, you can see people moving around, you can see cars driving, you can even make out the color of those cars, you can see houses, roofs, maybe you've even picked out your house before. But as the plane gets higher and higher, you can distinguish fewer and fewer of the little things, and the only things you can really make out are the big things. You get high and up enough, and maybe you can see the outline of huge fields, right? Or maybe if it's at night, you can see major roads that are lit up. So that kind of happens here too. As we zoom out on this graph, what happens is that the distinction of the bumps in here kind of go away, and you end up getting a graph that looks a whole lot like a power function. And where that leads us to is that in a polynomial function, even though in the middle, right, it does different things that is caused by adding and subtracting the lower powers of x or any constant, that a polynomial will behave at its ends like the power function that is made up of its leading term. So this is my leading term. That power function is called an end behavior model because it models or gives us a picture of how our polynomial behaves at the ends. Right? So let's look at how that works. I have my g of x function. Its end behavior model, which I'm going to write as g sub EBM, end behavior model. So this is not the same function of g, but it will model the end behavior of g, will equal the power function that is made up of its leading term. So if we think about the graph, right, of a power function with an odd positive integer, we expect that graph to look like this, right? Like y equals x to the third, y equals x to the fifth. And if we look at this and look at its end behavior, right, its limit as x goes to negative infinity is our left end behavior. And if we follow this graph off to its left end, it goes down to negative infinity. If in contrast we come in, this should be the limit as x goes to positive infinity, right? And we want to find this. This is the right end behavior. So we would look at the right end of this graph, and it is going up, which tells us its limit is positive infinity. Now, let's look at another example. So here we have this 6th degree polynomial with a leading term 3x to the 6th. So h has an end behavior model that is the power function 3x to the 6th. We know that the graph of a power function with a positive even exponent will look a lot like your parabola. So if we want to look at its end behavior, right, this limit as x goes to negative infinity, again, is my left end behavior. So if I follow this graph to the left, it's going up, and that limit is positive infinity. Right? My limit as x goes to positive infinity is my right end behavior. So if I follow this graph to its right end, it also is going up, and so that limit again is positive infinity. So I've got a table here which is just going to summarize the end behavior based on the degree of a certain polynomial. So if our degree of our polynomial is even, so for example, we have like y equals x squared, right? And the leading coefficient is positive, so this would be just a 1, or it might be a 2 or an 8 or whatever, right? Then our basic graph is going to look like, right, our parabola. And based on that end behavior graph, we know that the left end behavior, right, this is our left end behavior, will be positive infinity because our graph is going up on the left, and our limit as x goes to positive infinity, that is our right end behavior, will also be positive infinity. Now, if we have an even function, but with a negative leading coefficient, so that might be like y equals negative x squared, then the graph of our function is going to be this parabola flipped over because of the negative that's in front of it, which makes our left end behavior negative infinity because it's going down to the left, as well as our right end behavior. Now, if we have an odd degree polynomial like y equals x cubed with a positive leading coefficient, right, that's like having a positive 1 there, then our graph of an odd power function, right, with a positive, we'll have our little S-shaped curve here, and its left end behavior is going to be negative infinity because it's going down, and on the right it's going up, so that limit is positive infinity. If we have a negative leading coefficient, so we have something like y equals negative x cubed, then our graph is going to flip over that x-axis, right? And a negative cubed would be The opposite of a negative cubed would be the opposite of a negative, which is positive. And our left end behavior now is going to be positive infinity because it's going up on the left. Our right end behavior will be negative infinity. So the key really is not to memorize what's in this chart. The key is to know what the graphs of your power models look like, right? Graph them based on your leading term and determine your end behavior or your limits as x goes to positive infinity from those. All right, now let's talk about zeros of a polynomial. This is a very important thing to know, and that is that a polynomial of degree n will have at most n zeros. Our zeros, real zeros, are our x-intercepts. We can find the zeros by factoring, right? We can find the zeros by using the rational roots theorem, right, which we're not going to do. You can cheer. Woo-hoo. And we can find our zeros by graphing. So here's our first example. We want to find the zeros of u of x, which is defined as x cubed minus x squared minus 6x. So the first thing I'm going to do is I'm going to take that function, x cubed minus x squared minus 6x. My zeros are the x's that will make this equal to 0. That's why we call them zeros. So for me to solve that, I'm going to factor. First step of factoring is to pull out a GCF, which in this case is x. So I have x times x squared minus x minus 6. Right? What starts an equation stays an equation. That equals 0. Now, we have this quadratic, which we're going to attempt to factor. So I have my x, and then I'm going to take this, and that should have an x as the leading term in both of those binomials. And then if I go minus 3 plus 2, then my outers are positive 2, inners are negative 3. Those will add to give me negative x. And then my last give me negative 6. So that works. I want that to equal 0. So if I come in here, I have 3 factors. I have x. If that's 0, the whole thing's 0. I have x minus 3. If that factor's 0, the whole polynomial will be 0. And I have x plus 2. So I set each equal to 0. They each have x in them. So I end up with 3 possible solutions, that x is 0, that x is 3, or x is negative 2. Those are all real answers, right? So these are my zeros. They are also x-intercepts. So if I think about the graph of this polynomial, I know something about this graph. Right? So I know, let's come up here. I know that my graph will have an x-intercept at 0, it will have an x-intercept at negative 2, and it will have an x-intercept at 3. So I know my graph will pass through those 3 points. And we will add to this later. Okay. Now, let's try something else. So I would like to find the zeros of this function. So I'm going to take this and I'm going to set it equal to 0. My problem here is factoring, right? And we just don't have a good way of factoring that. We could use the rational roots theorem, but you have a calculator which will do quite well. So I'm going to go into my calculator. You should pause and do this as well. And I'm going to enter this equation. So I've got 2x to the 4th minus 3x cubed minus 12x squared plus 7x plus 6. And I'm going to graph this by doing a zoom standard. So when I graph this, what I see in my standard window, this is going from -10 to 10, both in the x and in the y direction, which leaves my axes centered, front and back. Then what I see in my graph is something that looks like this. And this is where you've got to be smarter than your calculator. My leading term here is 2x to the 4th. So my end behavior model, right, for v will be 2x to the 4th. And we know that an x to the 4th power function will end left and right. So what we see on this graph is that it is, right, should end left and right. So those are the ends. Right, the other thing that we have to fill in is that this graph is actually turning around and we have this VW shape. Okay? So if we use the 0 feature of our calculator, so we can do that to go calculate, so second trace, the second option is 0, and we move our cursor left of the 0. So as I move mine, I might move it to about here, right? I'm looking for this 0 right there, and enter that. Then it says right bound, so I'm going to move it to the right of the 0, so maybe about there. Right. Press enter. It says guess. Press enter again, and I get for this that x equals -2. And if I repeat that for the other 3 locations where I see this graph crossing the x-axis, I get zeros at -2, -1/2, 1, and 3. That's 1, 2, 3, 4 different zeros, right? And we could see that as a degree 4, right, we are looking for 4 zeros, 4 x-intercepts, or less. Okay, now, the next item that we're going to talk about is the number of turns. So this graph turns around here, here, and here. Those turns are also called vertices, right? That would be plural of vertex. And what is true of all polynomials of degree n is they will have at most n-1 turns. And those turns will happen between zeros or at a 0. So let's go back to our graph of u of x, which was x cubed minus x squared minus 6x. We knew from, I'm going to bring this up here. We knew from factoring that it had zeros at -2, at 0, and again at 3. Okay. We know that the leading term has a degree of 3, which means that the number of turns this could have will be at most n-1, which is 3 minus 1, which gives us 2. Okay. The other thing we can add to this is that for u, my end behavior model will be x cubed, which has the shape of our S-shaped curve, which tells us that our function is going to go down on the left and up on the right. So let's put things together. X-intercepts, -2, 0, 3. We know it's going to end up going down on the left, up on the right, and it has to have at most 2 turns. So if I think about this, if I start down, I don't have to start where I put this arrow, but if I start low, come through this x-intercept, turn, and then come through this x-intercept, I end up high. So I have turn number 1, turn number 2, and I have a pretty good sketch of my graph without having to do very much work. So let's do another one. We're going to look at v of x, which was 2x to the fourth minus 3x squared minus 12x plus 7x plus 6. Now we've already seen the graph of this. We did this just up here in these notes. But let's just look at number of terms that our leading exponent is 4. So the most number of terms we will have will be 4 minus 1, which equals 3. If we go back up and look at the graph that we saw, we had 1, 2, 3 terms. So that works. Now, another thing we need to talk about is multiple zeros. When we have a polynomial that is factored, okay, if that factor is repeated, so if I had something like x minus 3 squared, the squared tells me that factor is repeated, right? Those repeated factors produce what is called a multiple zero. Okay? So we would get a double zero, right? This would produce a double zero when we have that factor squared. Okay. If the factor is repeated an even number of times, so if this exponent is even, then what happens is, because squaring both a positive and a negative is positive, the values are repeated on either side of the zero, and the graph turns around at that zero. Okay? If the factor is repeated an odd number of times, then the graph is going to change concavity and pass through that zero. So what we would see here is that if I had a 0 at, say, 2, and it came from the factor x minus 2 squared, then my graph would come into 2 and turn around there. Okay? If, in contrast, I had a factor of x minus 2 cubed, I would still get a 0 at 2, but what my graph would do is it would come up to that 2, and then it would change concavity. It would turn around at 2. So, taking all of those things together, this is what we can do to graph a polynomial from its equation. We can, number 1, determine the end behavior, which is the leading term, right, which we can find by multiplying, taking the product of the leading terms if our polynomial is factored form. We find our zeros. We can find our y-intercept, which will be the product of the constants of each factor, right, and then pull together what we know. So here's an example. I have f of x is negative 2 times x plus 3 times x minus 1 squared times x minus 4. This is factored form of a polynomial. My leading term will be the product of the leading terms from each of my factors. So that's going to take my negative 2, my x, which is squared, and this x. So if I take negative 2 times x squared times x, I get negative 2x to the fourth, right? 1 plus 2 plus 1 is 4. Okay. That leading term leads me to my end behavior model for f, which is negative 2x to the fourth. Right? Think about the graph of that. You've got y equals x to the fourth, which will look like a parabola, but the negative 2 flips it. So my end behavior model graph will look like this, which tells me that the end behavior for f is down, down, negative infinity on both ends, right? So that's our end behavior. The next thing we want to look at is our zeros. So we're going to look at our zeros. So our zeros are going to come from what makes each of our factors equal to 0. Negative 2 is a factor, but it cannot ever equal 0. It's always negative 2. X plus 3 can equal 0 if x is negative 3. x minus 1 squared can equal 0 if x is equal to 1. And x minus 4 will equal 0 if x is equal to 4. So these are my x-intercepts. Finally, we're going to come in and we're going to look for our y-intercept, which is going to be the product of the constants from each factor. So if I come back and I want to find my y-intercept, now remember, you can find your y-intercept by just plugging 0 in for all your x's, but guess what's left? The constants. So I'm going to take this -2, that's a constant. I'm going to multiply that by this +3, that's a constant. And then I'm going to multiply it by this -1. I don't know why that won't stay. So we'll multiply it by this -1, which is squared. So we've got a -1, we've got to apply that power, squared, and then we're going to multiply it by this -4. Right, so -1. If I multiply all of that together, I've got -2 times 3 is -6. -1 squared is 1, so that doesn't change that product. And then I multiply that by -4, and I get 24, and that is my y-intercept. So putting those together, this is what we've got. So I'm going to erase this so I've got a little more room here. And I'm going to do a little sketch of my graph. I'm going to come in here and I know I have x-intercepts at -3. I have an x-intercept at 1. And I have an x-intercept at 4. I also know that I have a y-intercept at 24. And I know that my end behavior is down, down. So it's going to go down at the left and down at the right. Okay, now I have one other thing that I have to pick up, and that is that because this 0 of 1 came from a factor as squared, this is a double 0. And where I have a double 0, my graph is going to turn around. So I know that at 1, right, at 1, my graph is going to turn around. That's a little bit special. So let's see what we can do. If I start low, I come through my 3. I don't have to turn around at my y-intercept, but I have to go through it. And then I'm going to come turn around at 1. Hold on, something's not working here. Oh, no. My right end behavior was down, not up. So that's what my problem was. And I'm going to end down. And that's not a point perfect graph, but that's a pretty good picture of what that graph is doing, right? Without needing a calculator and without a lot of work. All right, here let's look at g of x. We're going to have to do a little more work here. But we're going to start by finding our end behavior model. So g end behavior model of x will equal the product of my leading terms, which is x squared times x to the 4th, which is x to the 6th. That graph, right, again, has left end behavior up on both sides. I want to find my zeros, that's going to be where each of my factors, I have x squared minus 4x plus 1 equals 0, and then I have x to the 4th minus 8x squared minus 9 equals 0. Unfortunately, I can't factor this, right? That won't work, but I could solve where this is equal to 0 by using my quadratic formula. So I have x equals the opposite of my b plus or minus my square root of my b squared minus 4 times a is 1 times c all over 2 times 1. What that gives me in the end is 2 plus or minus the square root of 3, which is about 0.268 and 3.732. Needed a little help from my calculator. So those are zeros though. Here, if I take this one, this actually does factor into x squared minus 9 times x squared plus 1. This x squared minus 9 will factor to x plus 3 times x minus 3, but x squared plus 1 doesn't factor. So still trying to find what makes that equal to 0, and that will be when x equals negative 3, when x equals 3, and this will never equal 0. So I don't get any zeros from there. So if I think about the graph of this so far, I know that my end behavior is up, up. I know that I have zeros at negative 3, at positive 3, right, at a little more than 3, so 3.7 plus a little bit more, and then at a little below, at a little above 0, right, so at 0.268. So I've got x-intercepts here, 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 and here. My y-intercept, let's put this up here. My y-intercept is going to be the product of my constants, which is going to be positive 1 times negative 9, which is negative 9. So I've got a y-intercept somewhere down here at negative 9. Right? I put all that together. And I can do a graph that fits that by coming down through here, coming up through here, turning here, and ending up. So that's finding a graph from an equation. Now we're going to go to the other direction where we find the formula for a polynomial from its graphs. And this is what we're going to do. So we're going to come in here, and we're going to start with the x-intercepts and find factors from those. Okay? So if the x-intercept is some number b, then the factor is x minus b. So if the x-intercept's a negative number, then you would do x minus a negative, which would be plus. If the graph turns around at the x-intercept, then you're going to put an even exponent, right? Use 2, unless you have a reason to know differently. If the graph changes concavity, right, so it comes in and lands and turns around there, then you're going to give it an odd exponent. Use 3, again, unless you know differently. We're not going to do this. We're going to take care of that a different way. And we shouldn't have to do this as well. We're going to take care of that otherwise. So here's an example. Okay. You have a graph that looks like this, and let's throw some numbers in here. So let's say that this x-intercept is at negative 4, that this one's at negative 3, this is at negative 2, this is at 4, and this is at 3. And notice we've got a turnaround there. So we're going to do this. We have zeros at negative 4, negative 3, negative 2, and 3 with a double 0 at know that because it turns around on the x-axis. So from those zeros, we're going to build factors. Okay, so I've got x minus my negative 4. I have x minus my negative 3, x minus my negative 2, and x minus 3, which I'm going to square because of the touch and turn. So simplifying that, we have x plus 4 times x plus 3 times x plus 2 times x minus 3 squared. My y-intercept is 4. That y-intercept is the point 0, 4. So this is what we're going to do. We know that our equation will equal will be y equals some number, right? There could be a coefficient there, I don't know what it is, times my factors, x plus 4 times x plus 3 times x plus 2 times x minus 3 squared. I know that my graph contains the point 0, 4. Right? We've done this before. So if I come in and I put the 4 where the y is, I don't know what k is, but then I put 0 where all my x's are. And I simplify that. I get 4 equals k times 4 times 3 times 2 times negative 3, which is squared, or 4 equals, right, this is 12 times 2 is 24 times 9 is 54. So I get k times 54. I solved that for k by dividing by 54. No, I'm sorry, that's 24 times 9. Well, let's do it this way. Okay? So I don't have to multiply that out. So I've got my 4 times these all together, which is 9 times 6, which is 54. So now when I divide, the 4's divide out, and I'm left with a k equals 1 over 54, okay, which gives me my equation, which is going to be y equals my k value, 1 over 54, times all of my factors, x plus 4 times x plus 3 times x plus 2 times x minus 3 squared. So the last example we have on here, we'll do in class together. I know this is just more than enough. It's really 2 days worth, but I kind of needed to get that in for you. So do a great job. I believe in you.